Pleased to chair your next session, which is going to be public key stuff, post-quantum, I remember. And the first speaker is Sebastian Faller. He's going to talk about the two-hash OPRF framework, and the taboo word is hash.
Thank you for the introduction. So the work I'm presenting was joint work with Bart Boelens, Lukas Dodgen, and Julia Hesse. The title already tells you it's some framework on how to construct post-quantum OPRFs. So the natural first question is, what are OPRFs? OPRFs is short, or OPRF is short for oblivious pseudo-random function, and it's a two-party protocol. There's a client and there's a server, and they want to jointly evaluate a pseudo-random function in such a way that the client has some input x, and the server holds the key for the PRF. And in the end, the client should learn the output of the PRF in such a way that the server does not learn on which points the PRF was evaluated. And the other way around, of course, the client should not learn which key was used. And also, the client should not be able to evaluate the PRF without the help of the server. You might think now, OK, why should I care about OPRFs? And it turns out that OPRFs have many cool applications. And one particularly interesting is the case of password authentication. And I'm going to show a quick example that should give you the motivation or the rough intuition for that. What you see here is how password authentication is usually done in the internet nowadays. You have a client who wants to authenticate. You have a server who pre-stored some salted hash of the password. Then you build a TLS channel. And the client sends the password attempt, PW prime, to the server. The server recomputes the hash and checks it against the stored value. There's one problem with this approach, and that is that the server sees the password attempt in the clear. You might think now, OK, this is not too bad because the password attempt might be wrong, why should I care? But actually, even a wrong password attempt might be very close to your actual password. But it could be even worse, like think of you're in a hurry, you try to type in your Facebook password, but you think about your banking password, then Facebook sees your banking password. Or even worse, you think you're connected to Facebook, but some TLS hijacking took place and you're actually connected to a different server, an adversarial server, and this server will absolutely be interested in all your password attempts. So what can we do about this? The solution would be to execute an OPRF protocol between client and server. So the client would put the password attempt into the OPRF protocol, and the server would use some key. And in the end, the client gets a high entropy version of its password, but the server never sees the key of the client. So in some sense, you can think of this as a way of like salted hashing, but the server never has to see your password to compute the salted hash of the password. And of course, like this is not the end of the story. Like you have to do a little bit more, but this is roughly the intuition that's behind the celebrated opaque protocol. OK, this is one application of OPRFs. There's many more. For example, WhatsApp is using them for their end-to-end encrypted backup system. You can use password-protected secret sharing, which is a nice way to like store your Bitcoin wallet securely shared on different servers and protected with a password. They're useful for single sign-on and private set intersection. That means they're pretty useful tools, so you would expect that a cryptographic primitive that is that powerful might be expensive. But it turns out in the classical setting, when you believe that the Diffie-Hellman assumption or Diffie-Hellman type assumptions hold, then it's super cheap to execute an OPRF. What you see here is the two-hash Diffie-Hellman protocol, and the name is the program, right? Like you hash twice, and you execute like a Diffie-Hellman key exchange, and you're almost there. So you have some, the client would, can I point to things? I'm not sure if you're seeing this. But the client would like blind the hash of its input, send it to the server would add the key in the exponent, and then the client can remove the blinding again. Super efficient. However, in the post-quantum world, the situation does not look that good yet. But people are doing research on it. Here's a quick timeline of OPRF constructions that are post-quantum secure and also have full security for server and client. There's even more cool literature out there if you also consider semi-honest security, but I will stick to the full security case. So there's been some work from Albrecht et al. In 2021 that showed it's possible. We can get OPRFs from lattices, but this was like a first feasibility result. In fact, they even showed that it's possible around optimal. Then later, people tried to use FHE, which decreased the network traffic by a lot. On the other hand, FHE is known to be rather computationally intensive, so the running time was not very practical yet. And this was basically the point when we uploaded our paper on ePrint, and you could see that we improved the network traffic even a bit more. Now, our protocol uses a bit less than 1 megabyte of network traffic, and we also have implementation that shows that the execution time of the protocol is below 200 milliseconds. But I said this was the situation when we uploaded on ePrint. Like in the last year, there were more constructions that appeared afterwards, and they're also pretty cool. I encourage you to check them out. There's 2 more constructions from lattices, one from standard assumptions, one from a new interactive assumption, and there's also a cool paper by Yang et al., where they use the same type of assumption that we use in our paper, and they get some nice batching properties. So you can see this is a vivid field of research. Okay, but what did we do? We did not just construct one OPRF, but in fact, we have a framework for constructing UC-secure OPRFs. And for that, we started out with looking at, okay, what does 2-hash Diffie-Hellman actually look like? And you can see here, that's the PRF that's jointly computed by server and client. And obviously, it has 2 hash functions, an inner hash function and an outer hash function. But there's also some function inside, right? If you don't think about the hashing, then basically what is jointly computed between server and client is h to the k. And the other thing that you need is a protocol for joint evaluation of this inner function. So this blind and unblind method that I just showed you before is, in some sense, an MPC protocol to compute this inner function, if you abstract it away a little bit. So that's what we distilled, basically. We have a theorem that shows you if you want to get UC-secure OPRFs, here's the things that you need. You need an inner function that satisfies 2 properties. The inner function has to be unpredictable, but it interestingly also needs a second property, which we call key collision resistance. It's a weak form of key collision resistance, and I don't have it on the slides, but intuitively it means if you're an adversary, it's hard to find 2 keys that collide on random inputs. Then you need somehow a multi-party computation protocol for this function f that you just analyzed, and you need 2 hash functions that you model as random oracles, and what you get is an OPRF. For this framework, we showed 2 instantiations, one from block ciphers, where the multi-party computation protocol could just be your normal garbled circuits protocol that you like. And we also showed a second instantiation from Legendre symbols, and this is the one I will focus on in this talk, because it turned out to be more efficient, and I think it's also the more interesting construction. So I already mentioned the Legendre symbol assumption twice, so here you have it. The first to conjecture that Legendre symbols are pseudo-random was Ivan Damgard already in the 80s. And what we use in our work is a formulation of this problem called the decisional shifted Legendre symbol assumption, which was proposed by Grassi et al. In 2016. And it says that if you take an input x and you shift it by some random offset k, that would be the key. Basically, what you get is a bit that you cannot distinguish between from a truly random bit. With that, we went further and said, okay, now we need to have this inner function. And like, if you go back, like this just gives you 1 random bit, but we want, say, 128. So we had to take a sequence of Legendre symbols. So h would be the input, k is the offset key, but now we also have to add these labels or random offsets to make sure that no 2 of the bits of the sequence overlap. So we really want independent bits in the output of this inner function. And if we plug the hash functions in that I mentioned before, then we're basically back to our 2-hash Diffie-Hellman blueprint that we wanted to have. So we have an inner hash function that is applied before you input the things into the inner function, and you also have an outer hash function that is applied after you executed your inner function. Okay, the next step, if you want to follow the framework, is you need to have an MPC protocol for this inner function. And the core idea is already there in the Grassi et al. Paper. If you would just have one of these Legendre symbols that you want to compute, then you can do the following. The client inputs its input x into some magic MPC box, and the server inputs its key. Then this magic MPC box computes x plus k. But it cannot output this to the client, because then the client learns the key, right? So what the server does, it also chooses some random s in the field, and then the MPC protocol has to square this s and multiply it with x plus k. And by this, you get a random masking. But the nice thing about Legendre symbols is that the Legendre symbol of x plus k is not changed by this, right? If x plus k is a square in FP, then s squared times x plus k is also a square, and vice versa. In the end, the client would get the value e, and now can compute the Legendre symbol on its own. It doesn't need to do this in the MPC protocol, but because of the blinding, the client can do this alone. The only problem we have here is that we don't just want one Legendre symbol, but we have to do it in a batched way and very efficiently. So what we use for that is vector oblivious linear evaluation, which is a cool MPC primitive where you have a client that can input some scalar h and a server that can input 2 vectors, u and v. And in the end, the client learns u plus h times v, so a linear function. And if you look at this, suppose the server would input u that looks like this, a u that's k plus the label that we need to separate the different bits, multiplied with s squared, and v is s squared as well. Then what the client gets is exactly h plus k plus l times s squared as we want. We have to work a little bit harder to get to the actual MPC protocol here, because I wrote, suppose the server does this, so you can already smell there has to be some zero-knowledge proof to make sure that the server does what it's supposed to do. But it was kind of tricky to get that from normal volley. So what we did is we defined something called volley plus, which outputs commitments on the inputs of the server. So these values that you see here, Cu and Cv, basically allow us later to compute a zero-knowledge proof that has a statement containing the secret values u and v of the server. Putting everything together, this is a simplified version of the protocol that we would get, and you see all the building blocks that we saw before. So the server computes u and v, as I said before, so u would be the key plus the label times s squared, and v would be s squared. It puts this into the volley plus. The client hashes its input, puts that into the volley plus, and because now we have commitments on u and v, we're able to prove in zero knowledge that the server was honest in putting its input into the volley protocol. In particular, that means we can make sure that v is actually a square, we can make sure that u is of the correct form, and that all the bits contain the same key. And in the end, the client hashes again. That's why it's the 2-hash framework. What we end up with, I promised you we get UC security, which is kind of a vacuous statement because it always depends on the functionality that you get. And we don't get the usual OPRF ideal functionality. We had to relax it a little bit to allow for delayed extraction of malicious keys. We believe this does not make much of a difference. We could prove that you still get opaque and PPSS from this weaker ideal functionality. and in particular, nothing changed for the honest server key. Like, this is a change that only applies to malicious keys. All right, then let's wrap this up. What you can see if you look at the paper is a generic framework for constructing UC-secure OPRFs. We show 2 instantiations of this framework, and we achieve sufficient security to plug these OPRFs into opaque or PPSS. The paper is available on ePrint, and you can also check out our implementation on GitHub. Thanks for your attention.
Thank you, Sebastian, for your interesting talk. Are there questions?
Hi, thank you for the talk. Could you expand a little bit more on what happens with the malicious keys? What are the consequences, and what can the server do?
Right, so the problem in the UC framework is basically that you have this outer hash function h prime, and a malicious server could choose some key locally, keep it for himself, compute peer or evaluations of this inner function for himself, start querying this outer random oracle on correct values, but at this point there was no protocol execution from which you could extract the key. And then later on, when the protocol is executed, your simulator would notice, oh gosh, like I should have programmed the random oracle before for the malicious keys. So basically we allow the simulator to delay this extraction until the point where the protocol is executed first.
This to upgrade the lattice space OPRFs to UC security?
There's a good chance that that works, right? Like basically you have to check if your lattice-based blinding protocol is an actual MPC protocol in the like UC sense, right? So you need your extraction properties, and it has to be unpredictable anyways, right? And probably it will be key collision resistant. So these are the 3 things that you would need to check, and then you get it. Yeah.
Any more questions? I think there is still a little bit of time. Yeah, there is. I'll ask mine. Oh, no, this is not. Yeah, so in the same vein as Martin's question, the assumptions seem pretty mild. Did you look at other possible ways to instantiate from lattices, codes, etc., etc., etc.?
Yeah, actually we didn't, and it would be interesting if you can get this unpredictability in key collision resistance, if you can get it from other assumptions, and I think, yeah, this is an interesting open question, yeah.
No more questions? Then let's take Sebastian again. I think we can wait 1 more minute because you're supposed to start at 5 if
Cool.
there's someone who wants to switch track. You're getting new audience.
Cool. Oh.
Okay, we're ready to start. The next speaker is Benjamin Benchina. I hope I'm not butchering your name. And he will talk about Hollow LWE, a new spin.
Yeah, hi, thanks for the introduction. So this is joint work with Martin and Russell, and it's on updatable public key encryption from lattices and codes. So there's a few ways to define it, but what we'll do is we'll just take a correct PKE scheme, and without modifying it, we'll equip it with two new algorithms, update PK and update secret key. So the first one takes a public key, it's a randomized algorithm, takes some randomness as well, and generates a new public key, and also outputs an update token. So this update token is then sent to the secret key holder, that the secret key holder can then use in update SK to update their secret key to a matching secret key. Right. So the correctness notion we require is that after every honest update, the new key pair is also valid, so it admits decryption correctness. And the security notion we consider is this extension of the CPA security notion called indistinguishability under chosen randomness, chosen ciphertext attacks, which essentially states that after a compromise, denoted here by a leaking of the updated secret key, old messages adversarially chosen, their ciphertexts remain indistinguishable. Right. The chosen randomness here refers to the adversarial capability that they get to essentially force the challenger to update the key pair with their chosen randomness. But as long as at least one update is honest, the old ciphertext should remain indistinguishable. Right. So let's look at an example of this. We'll do it from lattices because, as Luca put it, post-quantum stuff. So this is the dual RegF public encryption scheme. The key pair is essentially, well, what we'll call the lattice part, a matrix, and then a syndrome of some short vector R, and then the short vector R is the secret key. Encrypting essentially amounts to encoding the message into the last coordinate of an LWE sample, and decrypting is just removing the randomness and then rounding. The security is based on the LW assumption, but what really matters here is that this long-term secret key R needs to be sort of short enough for the decryption correctness to hold for this scheme. So let's equip it with the update mechanism from TCC21, which I think sort of illustrates nicely how these things usually go with lattices. So we'll update the key by essentially generating a new short vector and adding the syndrome to the old syndrome, and then to update the secret key, we'll essentially just add it to the old one. The update token here is the encryption of this update randomness. You can sort of verify it's just a summation that this is like a valid key pair. But the issue is that once you update this a few times, the norm of this new secret key R will slowly start increasing and increasing until after many updates it will eventually spoil, so it will stop being short enough to decrypt. To maintain correctness, what related works sort of do is they either restrict the number of updates to be sort of fixed, either 2 to 10 or 2 to 20, or they increase their parameters, namely they have a super polynomial module, the modulus Q, but this then implies large keys and large ciphertexts and so on, so it's not ideal. So we just asked ourselves, what if we just rotate the keys instead, so sort of instead of adding noise, which will slowly decrease the quality of the secret key in a way, what if we just rotate it with something that's norm preserving or angle preserving, so it sort of retains shortness. Right. Okay, so to sort of see how we did this, let's look at the lattice aspects of this dual RegF scheme a bit more. So a lattice is simply a discrete subgroup of R to the n. Here it's sort of generated by a basis of dimension k. We'll namely look at something called a construction A lattice. So we'll take a matrix over ZQ, and we'll essentially take a lattice that's generated by its columns, but we'll also add this Q times standard basis vectors, which will only really appear in the sort of non-systematic places. This lattice has this nice property. It's called Q airiness. Essentially, it is contained in the what I'll call the ambient lattice, Zn, and it also contains Q times Zn, so which essentially means everything is done modulo Q. Q for us is prime here. Right. So the LW assumption, in short, states that noisy random point for this construction A lattice for a random A is indistinguishable from mod Q from a random point from the ambient lattice. This is sort of the lattice bit of our public key. The secret key of the dual regf scheme is just a short vector in this lattice coset defined by this syndrome U of the kernel lattice defined by A. So we kind of look at this. So if we want to rotate the lattice, we'll also have to rotate the secret key, and then this last bit sort of suggests we might also have to update the syndrome. So by rotate, of course, I mean apply some lattice isometry. So two lattices are isomorphic or isometric if they are connected with an orthogonal matrix. So that's a real matrix whose inverse is equal to its transpose. In terms of basis, this essentially means that you can obtain a basis of one lattice by applying this transformation from the left and then maybe a basis change on the right. The problem we'll be sort of idealistically relying on is the lattice isomorphism problem, which states that deciding whether two lattices are isometric or maybe finding this isometry is hard. Here is a definition, the distinguishability problem from Eurocrypt 22. So this problem is sort of conjectured to be hard under certain circumstances, which won't matter today. Okay, so more concretely, what we'll do is we'll take our lattice part of the public key and we'll rotate it with a lattice isometry. We'll take the secret key, the short vector, and we'll rotate it with the same isometry. And then we also have to update the syndrome, and the correct way to do this turns out to be to just sort of apply this masking basis change to it as well. And you can sort of see that this retains this secret key equation that U prime is indeed a syndrome of R prime with respect to A prime. And you can, if you prefer, you can think of it as just completely randomizing a sys commitment, but like every bit of it changes, right? So the upshot, the good thing is that because these O's are isometries in the Euclidean metric, the L2 norm of R prime is exactly the same as the L2 norm of R, so that's great. But the issue is that these matrices are real valued. So even if we start with an integral A, like a QR lattice, or an integral short vector R, once we apply an isometry, this will in general not be integral, right? But to fix this, you sort of recall that all of these lattices are Q arrays, so they're all contained in this ambient lattice Z to the n. So what if we just limit ourselves to isometries that preserve this, this ambient lattice? And sort of the way to do this is to consider automorphisms of Zn, which are just lattice isometries that map Zn back to Zn, and it's sort of a well-known result, or just a product of a simple computation, that this is just the group of signed permutations. It's a finite group, and it's sort of easy to verify that this, of course, preserves Zn. It also preserves the scaled lattice Q to the Zn, and then it maps any Q lattice back to possibly another Q lattice, right? So that's good. It sort of also suggests that for our short vectors R, we're going to take signed vectors, so vectors that have plus and minus 1 as their entries. They are L2 short, and a signed permutation will map such a vector to another such vector, right? But at this point, you sort of have to be honest that you're essentially doing signed permutation code equivalence, right? So there's a sort of correspondence between constructional lattices of full rank matrices and linear codes over the finite field ZQ of length n and dimension k that are generated by these same matrices. And then the corresponding isomorphism problem is just the signed permutation equivalence problem, which sort of is also, under certain conditions, conjectured to be hard. So we sort of consider SPC to be like essentially lip, where we restrict our lattices to QR lattices and our isometries to signed permutations, right? So formally, what we do is our update public key algorithm simply rotates the lattice with some random isometry. Then we derive this basis change in some canonical way. You can think of it as HNF or systematic form if you're a coding theorist. And then we sort of update the syndrome with this matrix. The update token is simply just an encryption of this isometry, or to be more specific, a seed for it. And the secret key, what we do is just decrypt the update token into an isometry and then apply it to our old secret key. And this is sort of just the correctness equation. You see that because O transpose times O equals identity, this correctness holds. Right. But we have to be careful because the complexity of sign permutation code equivalence and just permutation code equivalence in general depends heavily on this special subspace of a code called the hull, which is sort of a product of the fact that the Euclidean geometry over finite fields is quite messy. So there are a lot of these degenerate vectors that are orthogonal to themselves in any code. And if such a vector is also in the code's dual, so it's basically orthogonal to itself and to any other code word in the code. And if there's enough of them, they form this subspace that's called the hull. And sort of, it's a known fact that permutation finding or deciding between two codes essentially boils down to deciding on finding permutations between their hulls. Right? So we have sort of attacks that are exponential in the dimension of the hull, but polynomial in any other parameter. So we kind of have to take care of this. Right? Essentially, because the dimension of a random code is small, in fact, most likely 0, SPC is easy on average. So we have to fix this. Right? We give an algorithm that, for a desired hull dimension H, essentially samples a uniformly random generator matrix for a code with that hull dimension. We call these codes or matrices H hollow, as in having hull of dimension H. And this sort of fixes this coding theory bit, but now we have to go sort of back to lattices and check that we haven't messed anything up. So we define yet another variant of LWE called hollow LWE, which is just LWE but on these hollow matrices. But we managed to reduce LWE to it in sort of a natural way. There's some loss factors that arise, but for us, this hull dimension H will be sort of relatively small. So all of this except the first one will be negligible. This first one sort of arises from the probability that sort of a uniformly random matrix that's full rank will have hull of dimension 0. We also adapt the leftover hash lemma to the sort of its hollow version. Essentially, it's the same statement as in Regev's paper. We just get this sort of extra slight increase in dimension, but this is sort of roughly bounded by 2k, so you can just think of it as like adding another bit to Q, or maybe increasing this LHL constant C slightly by 2 over log Q. Right? So this is not a massive increase. So in the end, our construction is then essentially just this dual Regev public encryption scheme, where A, instead of being sampled as random, are sampled to be H hollow. Our short vectors will be sort of signed vectors, and we use the above PC-based mechanism to update the key pairs. And we prove in the random oracle model that if you believe that this hollow LWE is hard, which you probably should since we reduce LWE to it, and that PCE on codes with hull dimension H is hard, then our scheme is secure in this int CR CPA model. Right. So here are some parameters. It's not great, but we are sort of working on ideas to sort of massively improve this. All right. Thanks.
Thank you, Benjamin. Very interesting. Are there questions for Benjamin? Don't be shy. One coming.
So if you want to put this in MLS, you need like a CCA security.
Yes.
Is there any challenge in achieving it, or just the useful proofs?
Currently, it seems to us that it's sort of just FO, basically. But yeah, we're sort of working on proving it in this, yeah. Okay, sense, yeah.
Is Ward coming for a question? No. I do have one. Can you just comment more on this table? HPS is the limited one you were explaining in the beginning?
No, this is from, I think, Eurocrypt 23. The one in the beginning is from TCC 21.
Okay. Okay, I think I managed to parse the table. What about speed of these things? They're super fast, I suppose.
Sorry?
What about speed performance when you implement these things? Are they super fast?
We didn't benchmark this, sorry.
Do you need random oracles, or do you use them for efficiency only?
Yes, we need it in the proof to sort of decouple these two problems. Yeah.
Thanks for talk. One reason for the previous work that can't achieve unbounded updates because the secret key is increasing. My question is, can we use binary secret key?
Sorry, can we use?
Can we use just a binary secret key? Just a 1, 0, 1, 0, 1, 0, 1.
In this scheme, or?
Yes, yes. In this scheme to achieve the unbounded update.
Well, here we have, I mean, plus and minus 1, which is essentially binary, right? Yeah.
And I have another question is that the separatist seems not can't achieve any capability because we can recover the previous separatist by the permutation, right?
Maybe let's take this offline.
Okay.
Then.
Okay.
Yeah.
Thank you.
We still have time for questions. I can have one more, if
Sure.
if you allow me. Is it so bad to have limited updates? Who wants more than 1 million updates?
Sorry, can you repeat that?
Is it so bad to have limited number of updates? Who wants more than 1 million updates?
Right. So, I mean, ideally, you would update with sort of every ciphertext, right? So then if you have say a long-living like group chat session that spans years, right, then you would kind of, I guess, reach that at some point, hopefully.
I'll count messages in my WhatsApp groups. Okay, are we done? Then let's thank Benjamin again.
Yeah.
We're gonna wait 2 minutes for the track switch.
It's not moving. Okay, sure. No worries.
Okay, it's time to start. So the final talk of the session will be given by Jad Silbach on binary codes in a computationally bounded world.
Thanks. So this is joint work with Daniel. And this talk is going to be about error correcting codes and cryptography. And we all know that error correcting codes are very important in cryptography. It has a lot of applications, such as secret sharing, hardcore bits, and etc. But this is going to be about the other direction. And that is to say, how can we use cryptography to get better error correcting codes? Okay? Now, the setup you should keep in mind is that we have some message M. We wish to send it through some noisy channel. And to do so, we're going to first encode this message, adding redundancy. Now, because this is binary codes, this code word is a binary string. And we send it through this noisy channel. The channel induces errors, but hopefully the other party can apply a decoding algorithm and recover the original message. Now, the rate of the code is the ratio between the length of the message and the length of the encoding. And of course, we want this to be as large as possible, because this would mean that we didn't add a lot of redundancy. Now, for detection, we're going to output both if the code word was changed. Now, classically, error correcting code are studied in the Hamming channels. And that is to say that the adversary can change any PN positions of the code. And this is an information theoretical adversary, right? The only limitation is the amount of error it can induce. However, in this work, we're going to consider computationally bounded adversaries. And by this, I mean the channel is a PPT algorithm, or possibly, or hopefully, a non-uniform PPT algorithm that can change any PN positions. So we have two limitations: the computational power of the channel and the amount of error it can induce. So this was introduced by Lipton in the 90s, and the rationale behind this is that this is actually modeling real-life behavior, right? Whenever you send something in real world, you're not going to be hit by a worst-case error. You're more likely to be hit by a computationally bounded error. And this is, if you're really interested about sending information from one place to another, then it makes sense for us to consider computationally bounded adversaries. And the hope now is, well, can we get better rates than what's possible information theoretically? Okay, so there's one caveat and one limitation, and that is to say, suppose you have a code that is good for non-uniform PPT channels. Then it turns out that this code is, of course, also good for information theoretical channels. So we didn't get anything from this relaxation. And the reason for this is, well, if the only limitation or the only thing you introduce is this computational aspect, by non-uniformity, you could just hardcore the distance between two close code words, and this could induce a decoding error. So the solution to this is going to be to introduce randomness, and this is something we usually do in cryptography, right? So we're going to enable the encoding to be randomized, and the decoding is only going to succeed with high probability. So nothing that you would not have expected. Good. So what about prior works? So classically, the first result was by Lipton, and he introduced a result using a secret setup. So classic results assumed some kind of secret setup. Lipton assumed a shared secret key. Mikhail et al. Assumed the public key infrastructure. But lately, there's been a push to actually try to construct these codes without a secret setup in the clear. And a recent result I had with Daniel last year, we were able to actually get optimal codes that achieved the best possible rate you can hope for under very minimum assumptions, one-way function and collision resistance hashings, even without a setup or any such assumption. However, the major caveat of this result was that it's only possible over large alphabet. It's large constant alphabet, but it's still large alphabet. So it's not binary. Another recent result is by Grossman et al., which introduced the notion of seeded codes. So seeded codes are, again, codes against information against computationally bounded channels, but these encoding and decoding functions also have access to some secret some public shared seed that is visible to everyone. So it's a construction in the CRS. And Grossman et al. Were able to give a construction for such codes under a very strong assumption that is only instantiated in the random oracle. Now, this work is going to be about, or going to focus on seeded codes. And specifically, we're going to give binary seeded codes under standard assumptions or better assumptions. Good. So again, let's just be on the same page. So what we are considering is an encoding and decoding functions. Both of them have access to some random seed. And this random seed is also given to the adversary or anyone else. Okay, and the notion of securities we're going to consider is as you would expect in cryptography, a selective notion and an adaptive notion. And in the selective notion, the message is chosen, then the seed is chosen, and then the adversary needs to figure out some possible noisy version of the code word of distance at most p. And what we require is that for any such adversary, that once you apply the decoding algorithm with the seed, you actually are able to recover the original message with all but negligible probability. And similarly for detection. And the adaptive notion is going to just be switching the order. First, you choose the seed, and then the adversary chooses the message and the damage code word. And we require the same things from the encoding, from the correction and the detection. Of course, the adaptive notion is the more desirable notion and implies the selective notion. However, it appears to be more challenging to construct. Good. So what's the main result of this paper? So the first result is that under LWE, we get the selective seeded or selective notion of security for seeded codes, achieving detection which is optimal. Right? We are able to detect up to half errors with rate that is essentially 1. This is essentially the best you can hope for. And the correction is that up to 1/4, we're able to get a rate that matches the best known list decodable codes. And this construction is matches or approaches the Bloch-Diablov bound. So I'm not going to actually specify what this specific rate means. It's kind of complicated expression. It's not very insightful. But just keep in mind that this is better than what's possible information theoretically. And what you should keep in mind is this example, for example, when p is approaching 1/4, the BZ bound is strictly greater than 0. However, the information theoretical bound is plummeting to 0. So for sufficiently large p, this is strictly better than what's possible information theoretically. So these codes are able or give us an ability to send information better than what's possible information theoretically. And this result could be extended, or we can get better rates if in the future someone actually constructs better list decodable codes. Okay? Good. So the second result is for or under a different assumption, which is, or we refer to as crypto dark matter. And this is based on the well-known result of Bonnet et al. And I'm not going to mention a lot or talk about this result. If you're interested, I'll be very happy to discuss this with you afterward. However, let me just say that this is a new assumption. However, it's kind of interesting. We think it might be interesting for other application. And under this assumption, we're able to get this adaptive notion of security. One caveat here was that this result only applies for sufficiently small p. However, I don't have sufficient time to talk about this. Good. So with the time I have left, let me just give you a general idea of how we can get the selective notion for seeded codes. Okay? And the ingredients we're going to use are two. The first ingredient is a hash function, which has some notion of security. And this is going to be some kind of two-input correlation intractability. And I'll specify what I mean by this in a bit. Okay? So we need some kind of hash that has this property of being two-input correlation intractable. And the second component is that we need some list decodable code that also has some structure to it. And this structure is going to be some decomposability or nested property. And specifically, what we require is that this code is generated by some matrix G. And G could be seen as like composed of two parts, an A matrix and a B matrix. Okay? And the additional property we require is that B itself is a subcode, right? So because this is a submatrix of G, this is a subcode of the code generated by G. And this B has distance half and rate that is 0. Now, not because we're sending less information with B, then obviously you can hope to get this, right? You can hope to get a larger distance with smaller rate. Okay? So these are the two ingredients we require. And the construction is very simple. The construction is going to be the following. So given a message M and a seed S, we're going to first encode the message, or we're going to encode M with S as follows. We're going to first take M, apply the hash on M, and take these two things and multiplying with the generating matrix of G. Okay? So note that we chose this as follows, so that when you apply, like when you multiply this by G, what you get is that A is multiplied by M, or sorry, M is multiplied by A, and the hash is multiplied by B. Okay? And the decoding is going to be the following. You're first going to apply the list decoding algorithm of G, the overall code. You get some candidate list of M prime, Y prime, right? Or MI, YI. And you're only going to accept, or you're going to output the message M, which is consistent. And by this, I mean you're going to check whether the hash of M with the seed is equal to YI. And what we were going to show is that with high probability, only one of them is going to satisfy this. Okay? Good. So the proof is going to go through two lemmas. The first lemma is going to show that the code actually detects from half errors. Right? So this specific construction is able to detect up to half errors, which is the best you can hope for. And the other lemma is kind of like saying, well, if you have a code that is at the same time list decodable and has this very robust decoding property, then this actually, or almost in a black box manner, you get error detection or unique decoding. Okay? So list decoding and detection actually translate to correction in this setup. However, okay, so this is kind of a generic thing, and it's kind of implicit in all previous approaches. So I'm going to focus on the first lemma. Okay, so with the time I have left, let me give you a general idea how we get this. Good. So the idea is as follows. So we have a code. So we want to show that the code detects from half errors. And keep in mind that the security key is a selective security. So what happens first is that the adversary chooses some message M. And then the seed is chosen and given to the adversary. And now the adversary needs to find some different M prime such that the decoding of M prime with S and the decoding of M of S are too close to each other. Right? If they are too close to each other and you have like half distance to go, then you could go from one code word to the other code word, and that you will not be able to detect which is which. Right? So it's kind of easy to see. So adversary is able to win or win the detection game if it's able to find two code words that are too close to each other when encoding with the same seed. Okay? And recall, right, that the encoding is just M of A plus the hash of M times B. Okay? So if I write this explicitly, this is just saying that the encoding of the first if M prime is like of distance half from the encoding of M. Okay? Okay, but now let me rearrange this term a bit, right? Let me take the M part, M prime of A, and move it to the other side, right? I can still do that. And still, what I get here is that the left part, which is the hash of M, or hash of M prime times B, is of distance half from this blue part, okay? So what do I have at the left side? The left side says that the hash of M times B, which is a code word of B, is of distance at most half or less than half from some string in the blue, right? So this means if I apply the decoding algorithm of B on this blue part, I'm guaranteed that the hash of S of M prime is contained in this list, right? Because by the list decoding property of the code B that is able to efficiently list decode up to distance half, I know that this hash is contained in this list, okay? So one way to think about it is that this is just some function that depends on M prime, and hash of M prime, and hash of M. And instead of having this thing here, I just have this efficient, I can have this condition written here that says the hash of M prime is contained in some efficient function of M of A plus the hash of B minus M of A, okay? So I'm going to define a security game, right? I'm going to define a security game that says the following. Adversary wins if it's able to find an M prime, right, such that the h of M prime is inside this efficient function, okay? And we call this notion targeted to input correlation interactability because it's a selective notion of security, right? It's a selective notion of security where first the message is chosen, and then the seed is chosen, and afterward the adversary needs to find another message such that it belongs to this function f. So it's a weaker notion than what you would expect generally for correlation interactability, but it's still a meaningful notion and might be useful, and as we will show in this paper. And what we show is that if the detection holds, then we can construct hash, we can construct a family, sorry. So the detection holds if we're able to construct a family that actually is hard to or satisfy this correlation interactability game. And in the paper, we actually show how to construct these primitives. Good. So again, this is a selective notion of security. This is weaker than the general notion. And what you should keep in mind, or what you should compare this to, is the notion introduced, or the functions introduced by Canetti et al., which constructed one input correlation interactable or CI family of hash functions under LWE for any f that runs in a priori specific n to the c sites. Okay? However, the translation from this to our result is not direct, because there is leakage. We have leakage on the hash itself, right? So f here gets some amount of leakage because it gets h of sm, which actually leaks some information on s. So we can just like use the result in a black box manner, and we have to actually work harder to actually get this result. However, we're still able to extend our result to get this. And what we show is that under LWE, for any fixed constant c, we can construct a hash family H, such that for any f of size n to the c and any PPT adversary, the adversary is only able to win the targeted two-input security game with all but negligible probability. Okay, so we get this. We're able to achieve this notion of security that we describe here. Okay. Good. So with this, let me conclude. And in this work, we showed that it's possible to get uniquely decodable binary seeded codes against any PPT adversary with the best known least decodable codes. And we get selective security under LWE and adaptive security under crypto dark matter. If you're interested in the second one, I'll be very happy to discuss it with you later. One of the new ideas is this introduction of this targeted two-input correlation interactability, which I think could be interesting or useful in other contexts. And as for open questions, well, can we get the adaptive notion under more standard assumptions? Can we get this from, or maybe a lot more assumptions other than LWE? And can we actually construct these codes for the binary case without any setup, without a seed, without a CRS? And as I said before, we were able actually to do so for the large alphabet case. So for large alphabet, we did not even need anything. We only needed one-way functions, and we were able to actually construct these codes. We did not need the setup or any of these things. Okay, so with this, I finish. I'll be happy to take any question.
Thank you very much, Jad. Very cool results. We have one question in here. I can just.
Thank you for the talk.
Thank you.
So, in one of your first slides, when you refer to your result on constructing optimal codes for you need large alphabets.
Yes.
And then, have you considered? Do you think it would be helpful to use, instead of linear correcting codes over finite fields, to use codes over rings, like, for instance, preparata, kerdoc, because in that setting, for instance, you have nonlinear code over C4 that are linear over certain rings under the Lie metric. That was actually the idea, to reduce the alphabet by paying a price with the linearity.
So could you repeat the first part of the question?
Yeah, so to replace just the usual error-correcting codes over finite fields with the Hamming metric by rings, codes over rings with the Lie metric.
So we did not consider this. I'll be happy to discuss
and
this
you can maybe check kerdoc preparata codes, or maybe to use rank metric codes instead of the Hamming.
Sure. So yeah, we could have used, like, I assume, like, we just wanted to stick with the most well-studied model out there. But I'd be interested to discuss it with you here.
Thank you.
Right.
Okay, I think we need to leave the floor for the next session.
Thank you.
So thank you again, Jad, and everyone in this session.